go over the last couple of announcements before we begin, since we are recording. Yeah. Press it and hold it down a little. Okay, now we release. Yeah, good deal. Okay. We're going to cover as far as we can in 8. This is the last section in 8. So if we finish this section, we'll go on and start 10. We skip 9. That's differential equations. It's another course. We'll get started on 10 if we can. I'll give you your exam at the end of the class today. That's where I was going to run off copies, because yesterday my office hours got blown up. I had to set up a lab for last night. I barely got that done before students started coming in, and I couldn't get anything else done before that next class. So anyway, I got a copy this morning. So what we'll be doing, what I'll do is, Marcus is here. I went on and ran off the whole test as if we finished everything. I'll just tell you which problems you can do, and then the others will be optional for bonus if you want to try them. So that's what it will be. So it's going to be a very short test. Sorry. I know y'all wanted a long one, but sorry about that. Okay. Then, next, your research papers are due in today. Anytime today. I'll be here probably until 5:15 or so this evening. Maybe later, but they're due today. If you turn them in tomorrow, you still get credit for them, but you'll have some points taken off for being late. So get them in. That can't be dropped, so please get them done. Okay? Have you done the student course evaluations? Not yet? Please don't forget to do those. Please don't. I've asked other students, and most of them tell me 5 minutes is all it takes. I'd say 5 to 10, depending on how. Say again? I can't hear. Yeah, okay. All right. Then, I think you had some questions, right? Okay. Okay, but you can ask. Let me find the copy of it so I'll know what you're talking about. Okay, this is the one that's evaluate the integral, right? All right, what's your questions?
After 5, I eat 5, but when I'm doing 5, I stop, I'm not sure what I'm doing is right.
Okay. So this is evaluate the integral from 4 to 6, dx over square root of blah, blah, blah. What's that? Oh, yeah. I returned those to her because she was in his. Test 1. And Theo, who's not here, be sure you don't let him see him, otherwise he'll get a better score. So, okay, that's 2. Did you turn in test 3 yet? Thought you did. Okay. All right. Just understand that some of these still out. Well, where is it? It starts calculate evaluate the integrals, right? I bet you've seen the grade on. Okay. It may be that I haven't finished marking it yet. Let me see. See, I got so many papers in yesterday. Yeah, that's probably it. I got so many papers in yesterday, I got behind in the grading. Okay. I have your score recorded. It's probably in this stack. Students were just piling papers everywhere today. Let me see if they're in here. All mixed up. There it is. It would be right near the bottom. Okay. Please don't share it. You can't change anything now, unfortunately. Okay. That was scary. All right. Number 5. Mark the page here. Number 5 is my memory around trigonometric substitutions. Okay? That would be similar to trying to find one like it. I would say okay, you got the old text. Yeah. No, that's not quite the same.
I tried to find something similar, but I couldn't.
What's that?
I tried to find something similar, but I couldn't.
Okay. Found something sort of similar.
Yes, I know.
No, that's still not as good as that. I'm sorry. Okay. The one that comes the closest is page 391. Looks like maybe number 26. No, 37. 37 is not far off. Actually, even closer is 40. 40 is pretty close. No. 37. Do you have that? Around page 392. It's in the 7.3 problems at the end of the chapter. What's your number? 37. Huh? Is that similar? It's not a definite integral, but I was looking for a definite integral, but I couldn't find one, so we can make it a definite integral. Is that okay?
Yeah.
Okay. All right, so let's do that. This is page 392. Let me get my pen activated. page 392. This is 7.3 exercises, number 37. Okay. And they give the suggestion there that's helpful. Okay. I think that's the closest to what we got. Okay. And this one is the integral of dx over the square root of x squared plus 4x. So yours is a minus 4x, but it's going to be very similar. Plus 13. Now, I cheated a little bit. I wrote the plus 13 out there. Here's why. If you'll notice the instruction there, it says by completing the square and then using a trigonometric substitution. All right. Now, do you remember how to complete the square? How? Half of 4 and square it. So you're adding plus 4, right? Right. But you've now changed the problem. Unless you subtract 4 right there. And now you haven't changed the problem. Right? Because you added 4 and subtracted 4. You're fine. Okay. So I'm going to rewrite that as the integral. Now, I'll put in the 4 to 6. I don't know if it'll work in this problem, but we'll try. We'll see. If it doesn't, we'll put in something else. Because this problem didn't have that. Dx over the square root of, and what is x plus 4x plus 4 perfect square of? X plus 2 squared, and over here you have plus 9. Very good. All right, now you can go back to that section if you wanted to. Okay. Exactly. Okay. So let u equal x plus 2, right? And du is equal to dx. Okay. So now what we've got is, well, okay, you got the integral. Now, here's what I was worried about here. I think we ought to change these limits. Well, we'll do that later. Let's not worry about the limits yet. Okay. So what were you going to say? This would be the integral of du over square root of u squared plus 9. And we can do that, can't we? Okay. As you'll notice, what your substitution is then, if you, where did this come from? Yeah. If you look back on just a couple pages at the summary, for the square root of u squared plus a squared, then your substitution would be let x equal, well, probably shouldn't use x, because that's already in the problem. Let's say again? Yeah, I know, but let's not use x. Pick me another variable. It can't be x or u. Give me something else. Can't be x or u. Give me something else. Say again? A? Okay. A is equal to, oh no, let's not use A, because A is already used to somewhere else. B, that sounds like a good one. We've got to have enough letters for this. B equal to, and here it says a tangent theta, but the a is the square root of 9. So it'd be 3 tangent theta, right? Then dB, which is a little strange, is equal to what? Yeah, 3 times secant squared theta, right? Right? Okay, no, all you have to do is then go in and, well, I like to draw the triangle too. If this is your theta, okay, the tangent of theta, this would imply that the tangent of theta is equal to b over 3, right? B is the opposite and 3 is the adjacent, right? All right. Now, oh, here's the d theta. Okay. No. I'm sorry. We didn't. You were right before. This is our u. Okay. I was thinking, where is that coming from? This is the u. You were right when you said that. Yeah. This is u, and then we're going to plug that in. Theta is the new variable, not u. Theta is. All right. So now we can rewrite this as the integral du is 3, I'm putting that outside, secant squared theta d theta. Now I'm hoping that is our monthly test, right? Okay, good. Or weekly test or whatever. That's not a, yeah, it's 10:01. That makes sense. Okay. Over the square root of, oh, let's also do this. Let's do what u squared is. U squared is 9 tangent squared theta, right? And then u squared plus 9 is 9 tangent squared theta plus 9, right? And that is 9 times tangent squared theta plus 1. And what's tangent squared theta plus 1? Secant squared theta. So this is 9 times secant squared theta. So that's what's in our radical. So the square root of that is 3 secant theta. So our numerator is 3 secant squared theta d theta. Our denominator has a 3 in it too. They go out. And a secant theta, it goes out. And so what we have here is the integral of secant theta d theta. Right? Okay. Now, this one, you either turn back to where we did it in 7.1, I think it was, or 7.2, or just turn to the back of the book under the trigonometric functions and look up secant theta, integral of secant theta. There it is. It's number 13 in the back. That's it. That would be the ln of secant theta plus tangent theta, right? I lost it. Yeah, secant theta plus tangent theta. Okay, and they put a plus c, but what you would do, okay, don't do that yet. Okay, you have to backtrack now. Okay, what is your theta? Your theta is the inverse tangent of u over 3. Okay, this is now a u. Sorry, remember that was U. Okay. Well, you don't have to do that. All you have to do is look at this. It's U. Okay. Secant theta is hypotenuse over adjacent. Okay. I'm going to erase some stuff here that we've already used. Hopefully it won't be too confusing. What in the world is that? That's already used that too. Okay. Hopefully that makes it a little easier to see. This will be the square root of U squared plus 3. Right? No, plus 9. Right? Which is your denominator. Okay, isn't it? So secant theta will be, this will be the log of, and I think we can lose the absolute value. We're in the first quadrant, everything's positive. It's the log of secant theta is the square root of U squared plus 3, plus 9, sorry about that, plus 9 over 3, plus tangent theta is U over 3, right? Okay. But now we go back and put what U is x squared plus 2. So that would be the, your final answer is log of the square root of x plus 2 squared plus 9. Wait a minute. Yeah, plus 9 over 3 plus x plus 2 over 3. Okay. And then you could plug in your x values. They're not going to come out very pretty numbers, but you could do it. Okay? Do for 4, and then you do. The limits, you don't need to. You're going to be okay. Because you see, they're just x's. So you can put those numbers in. Yeah. I don't know if this would help any or not.
It's really helpful.
Okay, good.
I came up to secant theta plus tangent theta, LA.
Right.
And then afterwards, I don't know how to use U or theta. Like, I can't.
Right. That's where the triangle's helpful. Okay. And by the way,
Can we
yeah, combine, like, this is what I was going to do. Log of x plus 2 plus the square root of x plus 2 squared plus 9 over 3. And then if you wanted to, you do the numerator minus log 3 if you wanted to do that. I mean, there's several ways you can go from there. But then what you do is plug in the values 4 to 6 or whatever. Yuck. Okay. Plug them in for 6, subtract off what you plugged in for 4. It's going to be messy.
Yeah.
Yours will probably come out easier than this. This one, those limits weren't picked for it.
This question is very close to the problem.
Right. Okay. Good. Any others?
I don't want to waste your time.
Okay. Well, it's up to you. If you want to ask, you can. If not, we'll move on. So you want to move on? It's up to you.
Is it okay after finish it? Okay. I'm sorry. Can you help me out with 6?
Number 6. Okay. Okay. see if we can find one like 6. I could spend some time trying to look for one like this, and there probably is, but let's just clear this out. Let's try a couple of things first. And when we get to a point where you're okay with it, we'll do that. Here is an integral from 0 to 1 of the square root of 4 plus x squared plus the square root of 4 minus x squared over the square root of 16 minus x squared, x fourth, sorry about that. Okay, dx. Now, without doing anything else, I'm going to try something that sometimes helps in problems like this, okay? It's called, rather strangely, rationalizing the numerator. You're used to rationalizing a denominator, but let's see what happens if we try to rationalize the numerator. In other words, multiply by the conjugate of the numerator. That would be the square root of 4 plus x squared minus the square root of 4 minus x squared. Now, I don't know if this is going to help or not. It's just a guess. And I'm going to do the same thing down here. You have to multiply that square root of 4 plus x squared minus the square root of 4 minus x squared. And I'm looking at this now and saying, no, it may not be a good idea. But we'll see. Okay. And then with dx. So that expression I just did was 1, right? And as long as x is not equal to plus or minus 2, you're okay. But it couldn't be because the first problem wouldn't have worked. And you see 0 to 1, and doesn't include any of those values, so you're okay. All right. The reason I did that, if you do this, multiply those two together, you get 4 plus x squared, right? Okay. Then if you do the cross products, the outer, the inner, they're the same, but one's plus and one's minus, right? So they disappear. Then you have minus, these two would be 4 minus x squared, right? Okay. So it really made the numerator a lot nicer. However, the denominator stinks now, okay? And by the way, if you do this, the 4's go out, and minus and minus is plus. That gives you 2x squared in the numerator. All right. I thought that might be helpful. It might not be helpful, okay? Because the denominator is now really messy. And that denominator would be square root of 64. Again, we're going to multiply those two together. That would be 64 as first times first. Outer would be plus 16x squared. The inner would be minus 4x to the fourth. And the last would be minus x to the sixth. And then you'd have minus the same type thing. 64 minus the 16x squared minus 4x fourth plus x to the 6th. Okay? Now, it was a try. I'm not sure it was worthwhile. It sure helped the numerator a lot, but it really messed up the denominator. However, let's look and see if a factor by grouping of the denominator would help. This would be 16 times 4 plus x squared. And this would be a minus x fourth. Oh no, that's just backing up and doing the same thing we just did, isn't it? Yeah, I don't see that's going to help us any. So that didn't work. Sorry about that. The other thing that you might try to do is rationalize the denominator. Okay? Marcus, did you get this one? Do you remember which technique worked? It's number, yeah. It's like number 6. Well, it is number 6 so far. But that is sometimes a technique will work. It just doesn't look like it's going to work on this one. So this time, let's rationalize the denominator. And it may or may not help, but let's see what happens. And in other words, in this one then, what we're multiplying through is, we just multiply the square root of 16 minus x to the 4th, square root of 16 minus x to the 4th. Because when you multiply these two together, you just get 16 minus x to the 4th, right? And up here you get something that's almost as bad as what we had before. It's very similar to what we had. That would be the square root of 64 plus 16x squared minus 4x4 minus x to the 6th plus, and the same thing with just a few. It's what? Oh, it's x squared, right? I forgot to put the square there. Okay. Since that didn't seem to help a lot either, then the next thing I think I would try to do would be something similar to what we did before, our trig substitution. But before we do that, I don't think that's going to be helpful either. But these are things to give a shot, see if it might help. Other thing maybe to do is factor everything in sight, okay? This would be, especially down here, the square root of 4 plus x squared times 4 minus x squared, right? Times, okay, and yeah, this may have some benefit. Hey. Okay, thank you. All right. I think this may have more promise. Okay. Leave them like that. Don't factor it any further. Okay. Now notice what you've got. The integral from 0 to 1 of the square root of 4 plus x squared over the square root of 4 plus x squared times the square root of 4 minus x squared, right? Plus the square root of 4 minus x squared over the square root of 4 plus x squared times the square root of 4 minus x squared dx. Okay? These go out here, these go out there, and now you have two that you can do. Right? That's it. Sorry about led you on the wild goose chase. Okay. Try things until they work. Okay. Find something that works. Any others? Okay. All right. All right. Now, where we left off then before or since or after or whatever, we were over on page in the new text 460, chapter 8, section 8.3. Let me clear this out of the way. All right. All right. Okay. Now, the verbiage that led up to this, we didn't quite get there. What we were doing before, the drawback for equation 2, which is the one we were using, is that it requires integration along the y-axis for your m sub x, okay? Which may cause difficulties if the lamina is defined in terms of the function of x, not as a function of y, okay? So therefore, integration along the y-axis doesn't work, okay? But there's a second formula for m sub x as an integral along the x-axis, and here's what it is. All right. Now what we're doing is we have a function y is equal to f of x. We're wanting, I mean, it's pretty easy to get your m sub x, because, I mean, m sub y. That's the moment with respect to the y-axis, because then it's the distance from the y-axis. That's x, that's f of x, everything's in x. But the moment with respect to the x-axis is harder to get, because it would be nice if you could do dy's here, but you don't have any dy's, because that function is only a function of x, and it's not a one-to-one function that you can get a function of y. So here's what you do. You break this into your dx's just like we did before. Okay? Pick a strip here. And then we're going to take and this is the lamina, remember, uniform density. That's the nice part, uniform density. So you know the center of mass of the m sub y, m sub x, which is the one with respect to distance from the x-axis, okay, for this strip is going to be the midpoint, okay? Well, since it's the midpoint, that's 1/2 of f of x sub j, okay? And so, because the shaded strip is nearly rectangular, center of mass has approximate height of 1/2 f of x sub j, okay? And then you do that for all the strips, and that's how you come up with your center of mass in the y-coordinate of the center of mass. The x-coordinate is pretty easy. The y-coordinate gives you this, okay? Now, you carry that to its extreme, and this is now when you can't express the m sub x as a function of y, like we did on the previous last time, what we do is use this. M sub x is 1/2 your rho, that's the constant density. I think in the new text, that's your delta. Okay? So in the new text, it's delta. In the old text, it's rho. So I'm going to go on and reduce this again and write delta in here and delta in there. Okay? Now, it's 1/2 your f of x. That gives you the location of the centroid, okay, for that strip, times the area of the strip, which is f of x times the x. So that gives you your f of x squared, okay. Now, if you had this as the strip in between two functions, then it would be this one, okay. If this is from the x-axis, it's that one. From between two functions, it's that one. So this gives you the formulas. Let's expand this back like we had it before. That's either a delta or a rho, whichever book you're using, it doesn't matter which, okay? It almost looks like a lambda. It's not supposed to look like a lambda. But these are the formulas. If you can't get f as a function of y, express f as a function of y, then this is how you do it. See, before, to do your m sub x, you had to get a dy. You had to get that as functions of g as a function of y. If you can't do that, then this is the one that you use for m sub x, if all you have is functions of x's. So, let's do example 3. This, I think, is example 3. Now, example 3 says, find the centroid of the shaded region in figure 14. It's figure 11 in the old book and figure 14 in the new text. Identically the same. Okay? Now, this one they didn't have to do that. You could have found the inverse function of that, but we're not. We're going to do it this way. Okay? And it said find the centroid. All right. That's the center of mass for a lamina. Okay? Shaded region here. Now, we can, okay. From the previous page, the m sub y is pretty easy. Oh, I can't write there. Okay. M sub y, that's at the bottom of page 458 or wherever that would be in your book. And listen, the delta, they didn't tell us what the delta was. We can assume it's equal to 1, and that's what they suggest you do. So forget about delta for a minute. Your units won't work because of that, but otherwise it's fine. So you're doing the integral, m sub y is the integral of x, that's how far you are from the y-axis, and the x is going, by the way, from 1 to 3. How far you are from the y-axis times the area of that little thing there, okay? The x is how far you are from the y-axis, and the length of that is e to the x, and the thickness of that is dx. This is e to the x, and this is dx, okay? There's your m sub y. Make sense? Okay? That one's not too bad to do. How would you go about doing that? No, not trig. It's a product of two functions, right? Which technique used kind of the product rule? Very first one we did. After substitution. Sorry, I was just going to say after substitution. Integration by parts, exactly. So what part you want to be what? let u equal which? X. And dv equal e to the x dx. Then du is equal to dx. That's easy enough. V would then be what? E to the x. Okay? And your integration by parts would take the uv, so this is equal to x e to the x. But because you have limits, you have to plug these in from 1 to 3 minus the integral from of the bottom line, e to the x dx. That's it. And that's also from 1 to 3. Okay? So when you plug in the first, that's going to be 3e cubed minus e to the 1. Okay? Minus, and what's the antiderivative of e to the x? E to the x, evaluated from 1 to 3. Okay? So that'd be 3e cubed minus e cubed minus a minus is plus e. E's go out, and this gives you 2e cubed. Right? That's your m sub y. Okay? Now, unfortunately, I don't have a lot of room, so I'm going to erase everything except that's what m sub y is. Right? So let's get rid of this. Okay. Hope you got it all down because I'm having to erase mine. Okay. Okay. M sub y is equal to e cubed. All right. Now I'll erase this last part. All right. Next. Want to do m sub x or m? I don't care. M sub x or m? Second? M. Okay, let's do m next. M, remember, it's just your mass. So that's, take that strip that we had before, and it's just the integral of e to the x dx from 1 to 3. Total mass of that. The density is 1. Okay? It's uniform, so we can just assume it's 1. If it wasn't 1, then you'd have a delta up there, you'd have a delta down here, they're going to cancel out anyway. So just assume they're 1. And what's this? I think we can do that. E to the x, evaluated from 1 to 3, and that would be e to the x minus e. Right? That's your mass. Now you're ready to do the m sub x. Okay. Now, again, you could have, let me just make sure they don't. No, they don't. Okay. You could have changed that to y's and try to do it from there. Just about as easy to do this. The only thing here, now your centroid of that strip there is m sub x would be, we're not going to deal with the rows here anymore because we're assuming those are 1. It would be the integral from 1 to 3. You're doing your dx. The dx comes into play with your area. Well, the area is e to the x dx. Okay? The only difference there, your centroid here, is 1/2 of e to the x. So you can put the 1/2 out there, and that would be e to the 2x. Okay? But you also have an x in there, don't you? No, that's it. Okay? 1/2. So there it is. So can we do that integral? What would that be? Have the 1/2 out here. Okay, the antiderivative of e to the 2x is going to be e to the 2x. But then you chain rule, you're going to have another 1/2. Right? Okay. And then we'll evaluate that from 1 to 3. So that's going to be 1/4 e to the 6 minus e squared. There's your m sub x. All right. Now, what we were looking for is the centroid. So the x bar, the x coordinate of that is going to be your m sub y, 2e cubed over e, what did I write here? Dumb. That's a cubed here. I wrote an x for some reason. Okay. Over e cubed minus e. Okay. We can simplify that a little bit, not a lot. Factoring e out of the denominator, you'd have 2e cubed over e times e squared minus 1. That would make this e squared up here. I don't know if that's any simpler, but it seems a little bit. So, all right, your y bar is m sub x, which is 1/4 e6 minus e squared over m, which is e cubed minus e. Okay. I think we can simplify that a little bit too, because that is 1/4 e cubed plus e times e cubed minus e over e cubed minus e. Those go out, and there's what your y bar is. Okay? Well, let's plug some numbers in and see how it looks. Okay? If you plug in, well, just evaluate. Get your calculator and do 2e squared, e to the second power. Now, supposedly, my cell phone will do that. I'm not sure I know how to do it yet.
I got the same answer.
I'm sorry?
I got the same answer.
Oh, you did. Good for you. Okay. What did you get those answers to be? X bar was?
2.3130.
Let's just leave it like that. And this one was? Y bar? 5.70. Let's just leave it there. All right, let's see if that makes sense. Okay, 2.3, let's just, okay. 2.3 would be somewhere about here, right? There would be 2.5, 2.3 would be somewhere about here, okay? And 5.7, there's 25. That would be 12.5. That would be 6 something. So your 5 something would be somewhere right along there. So yeah, it looks like right about in there. That's where your centroid is. And that seems reasonable because it's weighted that way and weighted this way. Because more of your mass is on this end and more of your mass is on the bottom. So yeah, that looks pretty reasonable. Okay? And you say that is what they got in the book? Good for them. I'm proud of them. Okay. They didn't simplify like I did, but they could have. Did you use their form or my form when you evaluated? Theirs, okay. I just wanted to see if mine was right. Okay. All right. Now there's another, oh, that's all right. You don't need to do that. It's 2e squared divided by parentheses e squared minus 1, close parentheses, equal. calculator as a phone. A phone as a calculator. I never have had much need, but now I do a little bit. What's that? Same? Good deal. All right. So let's move on to the next issue, and that's this one. If you have a lamina, remember that's uniform density, that's symmetric about an axis, x-axis or y-axis, then guess what? You know the center of mass is on the axis of symmetry. It doesn't even have to be symmetric about an axis. If it's symmetric about anything, it's about the center of mass has to be on the axis of symmetry. Because if all of your masses or the densities are equal in here, and this is identical to that, you know the x coordinate of the center of mass has got to be 0 in this case. Or if you had this over here at some other place, wherever that axis of symmetry is, center of mass has got to be on. Down here, wherever it was, it's got to be on the axis of symmetry. Because you got the same mass over here as you do there. So center of mass will be there. The problem then is just figuring out the y component of center of mass. You already know the x component. Now, if you had something centered on the symmetric about the y-axis, about the x-axis, then you know the center of mass is going to be on the x-axis. Or along any horizontal axis, you know the center of mass is going to be on that axis. But they have to be symmetric. It has to be a lamina, thin plate. Okay. Now, that leads to the theorem 1, which is the symmetry principle, which is if a lamina is symmetric with respect to a line, any line, okay, guess what? It could even be a slanted line. If you have something symmetric with respect to any line, the center of mass is going to be on that line. The centroid lies on that line, okay? So I think we're ready for example 4. Now, frankly, the figures don't quite look the same, so let me read this and make sure we got the same problem. Find the centroid of a circular half disk of radius 3. I believe, yeah, it must, is that what yours reads too? The centroid of a circular half disk of radius 3, or is it a wire that's a radius? It's a circular half disk. Is that right? A circular half disk of radius 3. Okay, fine. My memory was we had a wire that was in the shape of that, but if that was a different problem. Okay, looking at this, I couldn't tell. Okay, so here we go. Now, they didn't say where you had to draw it, so we drew it whose center was at the origin. As soon as you do that, you know the centroid. Now, if that was a whole disk, I could tell you where the centroid was. It'd be in the center, okay? But it's a half disk. But I can tell you the x-coordinate is going to be x equals 0. Because you got the same mass on one side as you do the other, everything balances out. Now all we have to do is figure out the y component of that centroid. Now here is a semicircle. They gave you this, the square root of 9 minus x squared, okay? That gives you that as a function of x. All right? Now, oh my goodness. My head's so clogged up. Okay. That's the graph of your semicircle. The boundary of it, square root of 9 minus x squared. They have to be plus or minus to have the other half, but we're not doing that, we're only doing the upper half. Okay. So, We don't need to do the x. We know the x is equal to 0. X, center of mass, is 0. So if we are going to do the y, let's strip like this. Okay? And we're going to need to, I'm just about exhausted with not being able to breathe. Okay. If we do this, it's going to be a dx. Okay? The y component, we would like to have it like this, but that's going to be really nasty. Okay? So let's do it the same way we did before. Let's take the centroid of that piece right there. Okay? And we're going to sum all those up and see what our centroid is. Okay? So the y component will be the m sub x. We'll use that formula we just had. M sub x is equal to, and we're going to assume our delta is 1 because it's all going to come out in the wash anyway. Okay? So it'll be 1/2 the integral. Okay. Now here we have another little dilemma here. If you do this summation over the entire thing, you know let's write it down. It's 1/2 the square root of 9 minus x squared. That's the height. 1/2 the height times the height times the width. So basically, or that function squared, that's what the function squared is, dx. Okay? Now, this was if it's going from -3 to 3. But guess what, folks? The centroid of 1/2, the y component of it, is going to be, see, this is the even function done over a whole thing. So I think all we have to do is double from 0 to 3. I think that's the case. Let's try. I don't think let's try it and see if we get the right answer. Okay? So what we're going to do is double that, so you lose the 1/2 of 0 to 3, 9 minus x squared dx. What's the antiderivative of that? 9x minus x cubed over 3. Evaluated from 0 to 3. Let's see if this works. I think it should. Everything in me thinks it should, but I may be wrong. So let's try it. 9 times 3 is 27 minus 27 cubed, the thirds. Okay, and then minus 0, I'll do that one. So this would be 27 minus 9 equal 18. Okay. Yeah, we got the same thing. Okay. That only gives you m sub x. What else do we have to do? M. Yeah, you got to do m. Okay. Well, guess what? We haven't done that yet. Okay. Now, do you have to do your other thing, or can you just, this is just the area of a semicircle. Do we know what that is? Area of a circle is pi r squared. The r is 3, so that would be 9 pi. Well, guess what? The area of a semicircle is 9/2 pi, half of 9 pi, right? So there's your mass, okay? We've gotten off really easy, haven't we? So our y bar is going to be your m sub x, 18, divided by 9/2 pi, Well, that's the same as 18 times 2 over 9 pi. Well, this will go twice. That's 4 over pi. Sure enough, that's exactly what we got. 4 over pi. Does that make sense? Did any of my cheating steps bother you? Okay. You're okay with it? Did they do the same thing about the area? Yeah. They just did it. 1/2 of the area of the circle. All right. The next one isn't quite as straightforward, but it's still here. Okay? Now, we're using additivity and symmetry here. All right. Here's our problem. Uh-oh, came out almost right on the money here. Find the centroid of this region. It's figure 17 in your book, figure 14 in her book. Okay, same figure. Okay. Now, what is this? This is an isosceles triangle whose base is 4, whose height is 3. It's not I don't think, I'm pretty sure it's not an equilateral triangle. Okay? Because that wouldn't work out. Okay? But on top of the isosceles triangle, balanced perfectly up there, is a circle. And that has a radius of 2. Okay, so its radius is the same as the boundaries there. Now, they say here the moment of the region R, which is the entire shape, is the sum of the moments of the triangle and the circle. Okay. Now, right off the top, can you tell me, because this is a lamina, okay, we're looking for a centroid or a moment, the density, they haven't said anything about density. We assume it's going to be 1 then. What will be the x component of that centroid? The x component of the centroid. Because this is exactly balanced here, this is exactly balanced there, it's going to be 0. X component is 0. Symmetry. It's got to be on that line of symmetry. Everything on the right is balanced with everything on the left. It's got to be that. So we know the x component. Done. Now we got to get the y component. Okay? So what we do with the y component, there's a couple of ways you could do it. Okay? Let's do the circle first. That's so easy. Okay. What is the y component of the centroid of the circle? It's the center of the circle. It's the exact plane. So its centroid of the circle itself is 0, 5. Okay. But it's not the centroid that's additive. It's the moment of the region. It's the sum of the moments of the triangle and the circle. Okay. So if we can find so we really don't need to know the centroid of the circle. I got you off there. We need to find the moments. Okay. We know the x component, so we don't have to do any m sub y's. So all we have to do is m sub x's. So let's do those. M sub x for the triangle. That's what we're doing now. Now, how do you want to do that? M sub x would be, if we did strips this way, dy's. I don't know if that's the easiest way to do. Oh, and by the way, they do the triangle up top. I wrote it down at the bottom. It doesn't matter. Okay. Now, burr. Okay. They start with a moment of circle. We'll come back and do that because it is so easy. Let's do it for the triangle. Okay. Now, if we were to do it this way, your distance from the x-axis, of course, is y. Okay? That's the distance from the x-axis. And y is going from 0 to 3. And this is your dy. Okay? What you need to know is the length of this thing. Okay? Now, by similar triangles, 3 is the 4, right? The height here is to the width there, as this height is to this width there. Does that make sense? 3 is the 4, as this height is to that length. That's what we're looking for, that length, right there. So that height there would be 3 minus y. That's this length right here, 3 minus y. And the width here, that's what we're looking for. What do you want to call that? W? I mean, I don't care what you call it. I guess they call it L, so let me call it L. Okay, what is that length L? That length L would then be 12 minus 4y divided by 3. See how you get that? 3L is equal to 12 minus 4y. Cross multiply, proportion, right? Divide by 3. So that's what this length is here. Okay? As y goes from 0 to 3. Because when y is 0, you're at 4. When y is 3, you're at 0. Yeah, that seems to work. So your m sub x for the triangle is the integral of y times 12 minus 4y over 3, that's the length, times dy. That's it. Okay? So what we can do to make this a little simpler, pull out the 1/3, the integral from 0 to 3 of 12y minus 4y squared. Oh, wait, why do we do that? Let's pull out a 4 too. And that would make it 3y minus y squared. You see what I did there? Take out the 4 out there, 3y minus y squared dy. I think we can do that integration, can't we? 4/3 antiderivative of 3y. 3y squared over 2, right? Minus y cubed over 3. Evaluate that from 0 to 3. I'll do the 0 part later. Okay. Be 4/3. And this would be 3 times 9 is 27/2, right? Minus 27/3. Okay, I'll do the 0 part. Done. Okay. Now, least common denominator here must be 6, right? So this will be 81, 3 times 27, minus 54 over 6, right? Okay, times 4/3. Okay, now guess what? 2 will go into 4 twice, 2 will go into 6 3 times. So that gives me 81 minus 54, I think is going to be 27. Is that right? 81 minus 54? 27 over 9, which is going to be 3. Whoa! Is that m sub x is equal to 3? I'm sorry, m sub x for the triangle is 3. No, they get something else. No, wait. They got 6. How did I blow that? Okay, let's see. What I was using for L, okay, y times, oh, okay, they did 0 to h. That's disturbing. Oh, wait. I had a 2 out here. 2 times that. That is 6. See, when I cancel that out, it's 2 times that, 6. Woo! Okay. Now, they did it differently, but we got the same answer. So there's your m sub x for the triangle. Okay. Now, the m sub x for the circle, that's the piece of cake. That's what I was going to say before. M sub x for the circle is 5. You see it? It's right there. It's got to be that 5. The center of mass for the circle is 5. Sorry. Okay. So you add those two together. So your m sub x for the whole region, what did they call this? R, I don't know what it is. For the entire thing is, oh, I'm sorry, wait. Sorry. M sub x is not 5. The y bar for the circle is 5. Sorry. Okay. But the y bar is equal to m sub x for the circle over m for the circle, right? What is the mass of the circle? Yes, 4 pi. So this will be 5 is equal to m sub xc over 4 pi, right? So m sub xc is equal to 20 pi. Okay. So this is equal to 20 pi. Your m sub x for the triangle is 6, So the m sub x total is 6 plus 20 pi. Okay? Now, we take the m sub x and divide it by the total mass. Well, we already determined what the total mass of the circle is, didn't we? Well, no, we didn't quite, but we came awfully close. Yeah, we did, 4 pi. There it is. So m for the circle is 4 pi. What's the m for the triangle? Okay, I'm going to clear my drawing out of the way here. Let's just do the mass of that triangle. M for the triangle. What is the area of that triangle? The base times the height. The base is 4, the height is 3, half of the base is 2. 2 times 3 is 6, okay? Not only is the moment for the triangle 6, but it's also the mass of the triangle is 6. So the y bar for the whole thing, not just the thing, is equal to the the m sub x for the whole thing over m for the whole thing. M sub x was 6 plus 20 pi, and your mass for the whole thing is 6 plus 4 pi. Okay? You can simplify that a little bit by factoring out a 2 out of the numerator and denominator, and that would be 3 plus 10 pi over, factor out a 2 there, 3 plus 2 pi. Okay? They didn't do that. They just went right to the thing. But if you'll take those numbers, 3 plus 10 pi, divide that by 3 plus 2 pi, what do you get? Same thing. Approximately 3.71. Now let's see if that makes sense. We know the x-coordinate of the center of mass is 0. The y is a little bit above here. That would be 5 here, 3, 5. That would be 4 in the middle. Be right about there. Okay. This would be 4, and 3.71 would be somewhere right about there. Does that make sense? Yeah, because you see the circle has more mass than the triangle. So the center of mass is going to be a little bit higher. Not much, but a little bit. Okay? Does that mean you're getting close to time? What time is it? It's 11:10. 11:08? Okay, we got 2 minutes. What can we do in 2 minutes? Oh, this is how they went about doing their triangles area. Since you had an isosceles triangle, why go through all that? It works, but you can do it if you want to. This would be any old triangle, this would work. We had an isosceles triangle, so we didn't have to do that. We got the same answer. The theorem of Pappus is mentioned. The drawing is showing first on here, which is sort of bad. This is Archimedes' law of the lever. This is on page 462. Oh, they don't show. Okay, theorem of Pappus doesn't show in your book, does it? Theorem 2, theorem of Pappus. Okay, it is in your book, but since it's not in hers, we won't even mess with it. Actually, it shows up somewhere else. I know it does. But we're out of time anyway. But Pappus would be a decent paper topic if you haven't chosen one. I think both of you turned them in already. So, yeah, you don't need to. But then Archimedes would be too. Theo out there, if you're listening, those are 2 more possible paper topics. Okay. Now, let me give you your test. Okay. Oh my, I'm so stiff. Sitting too long. Okay. Now, I apologize ahead of time. The test is too easy, too short. Sorry about that. Okay. I thought we were going to get further today, but I didn't realize we would have questions, which I don't mind answering questions. But I probably wouldn't have done it this way then. But you're required to do for your test, for your final, 1 through 6. And by the way, 1 and 2 are from section 8.1, 3 and 4 are from 8.2, 5 and 6 are from 8.3. Now, if you want to, look at chapter 10, sections 1 and 2, and chapter 11, 1 and 2. And if you look at those two and can figure out 7 through 10, they're bonus. Okay? I think there's maybe a little bit of a misprint on 7. Let me check. I don't see where my limit is ranging from. I think it's as n is going to infinity. For sure. Could be. I think that's what it is, but let me go and check that. But you can try those. If you don't want to try them, that's not going to hurt you. Neither right answers are yeah. I'm pretty sure that says n is going to infinity. Let me just check. It may be, it doesn't matter. Yeah, that limit is n going to infinity. Number, what was that? 7. The limit is n is going to infinity. All right. That wraps it up. Enjoyed having y'all. We'll look forward to getting the finals in. You've already turned your papers in. And the other thing is, don't forget to do the course evaluations. Okay. Maybe, I don't know if we want you to graduate or not. Okay. All right. Yeah, did you have a question? Oh, yeah, when is it due? Good question. Anytime next week, Monday through Thursday. I mean, if you finish it tomorrow or Friday, you can turn it in then. But anytime next week, Monday through Thursday. Technically, they're due Wednesday 9 to 10:50. But you can turn it anytime. You can't turn it in on Friday. I'm here only until 8 o'clock Thursday evening because we're leaving town on Friday. So you've got to get it to me by the end of business on Thursday, because I have to have grades in by Monday noon. So get it to me sometime next week. If you finish it today or tomorrow or Friday, turn it to me then. Friday I'm on the Birmingham campus this week. Next week I'm here on this campus, Monday through Thursday. Anytime then. Okay. All right. Good deal. I'm recording all